Our next speaker is Balt van Rees from École Polytechnique, talking about lightcone and modular bootstraps. Thank you.
Okay, great. Thank you, Boris. So let me begin again by thanking the organizers for organizing a very nice conference and giving me the opportunity to entertain you for the next 40 minutes and make you all forget that you're very hungry and really want to go for lunch. So I'll talk about some rigorous, precise, mathematically precise results in the context of the lightcone and the modular bootstrap based on so these two papers and some work in progress. So to get everybody on the same page, let's just recall what is the lightcone bootstrap. Maybe some of you have not even seen this before. So we're going to look at conformal field theories. We're going to look at a 4-point function of some operator, some scalar operator, say phi. And of course, by conformal invariance, I put my points in the canonical configuration. Z bar are just complex coordinates on some two-plane. I'm in d greater than 2, but you put all the 4 points in one two-plane, of course. And then you get this expression, and Jeze had a similar expression on her slides. And this function g, which depends on z and z bar, has, of course, this famous conformal block decomposition with some coefficients lambda p, and for every conformal block, there's a scaling dimension delta and a spin j, and so on. So that's a bit too complicated for the purposes of this talk. So let me just replace this conformal block basically by its leading term. So we're just looking at monomial decomposition again for the purposes of this talk. So I call this a toy conformal block, this is the monomial, and then I get the decomposition like this. Actually, this decomposition exists in any CFT because I can just decompose the block into monomials. I get the same. It works too. So what can I say in a general CFT? If I look at this monomial decomposition of a 4-point function, well, it's due to the operator product expansion, and the operator product expansion converges. So this thing is supposed to converge for at least in the product of the disk, where z and z bar have both modulus less than 1. There's unitarity. I'm going to assume unitarity. And so that means that all these coefficients c and these exponents h and h bar are strictly positive. H and h bar are related to the scaling dimension and the spin, of course, like so. Then there's locality. Spin should be integer. So in my language, that means that h bar minus h is also an integer. And of course, there's the famous equation of CFT, the whole starting point of the conformal bootstrap, this crossing equation, which says that, well, this is just symmetric on the permutations of the operator and have this funny prefactor here. So this crossing equation follows from just Bose's symmetry, basically. Okay, so this is my setup. Now let's take the lightcone limit, right? I want to answer this question, what's the lightcone bootstrap? So the lightcone bootstrap is the following question. If I take the lightcone limit, I see this behavior of my correlator, and then there's some subleading corrections, and I assume this lowest value h bar min is strictly positive. And you have this behavior, and you have this type of sum. And the question is then, well, what can I say about the coefficients of the sum just from this behavior? That, in a nutshell, is the lightcone bootstrap. If you want to be fancy, you can take into account, if you have answered the question to leading order, you can try to see what happens at subleading order, and so on and so on. Right? So that's the thing we're trying to, that's the kind of game we're trying to play. So, okay, let's put on my physicist hat for a minute and say, well, what can we expect? Let's not be very precise. So here's the equation from the previous slide, and let's do an imprecise analysis. Well, I say, okay, I have the z bar to 1 behavior, so that corresponds to large h bar, right? So this is important because large h bar, right, here I wrote it again, j is h bar minus h. Large h bar, h finite means large spin. So we're going to say, by construction of this limit, something about the large spin limit of any CFT, because this is true in any CFT. Secondly, well, this right-hand side has its own expansion in monomials. It just looks like this, where this is some Pochhammer symbol, and there's some factorials, so the coefficients, the exponents completely known. So roughly speaking, the physicist would say, well, this green summand should roughly become this red summand in the large spin limit. That is the conjecture. So what does this look like pictorially? Well, here's a little example. So the red spectrum are these red crosses, right? So I plot here h vertically, and instead of h bar horizontally, I just put j because that's a nice integer, right? It's m minus n here. Of course, j also goes in the negative direction, but that's just the same thing. So these reds in summand has terms just at the crosses, and so we're expecting that in any CFT it looks a bit like the green dots, right? So here I've sketched 3 trajectories, but of course this goes up all the way. This should not be 2 delta phi. This should be delta phi plus 1, delta phi plus 2. But that's an error from. So you expect, right? I've sketched here 3 trajectories, but if you look closely, I've sketched 3 slightly different behaviors. So for example, for the first trajectory, you just have things as expect, right? You have an operator, a monomial for every spin, and then gradually, for larger and larger spin, things become more and more like what you expect the red crosses to be. But in the second trajectory, I've omitted the spin here. And okay, maybe at spin 6, yeah, there might not be an operator, right? This is some asymptotic statement. But maybe there's also something omitted at spin 9 and spin 12 and spin 17 and spin 10,000, right? There could be an infinite set of missing spins. Is that allowed? Is something like this allowed? Is it still consistent with this behavior or not? Or here in this third trajectory, I've sketched a little bit of a different thing where sort of on the average, there's an operator at the red point, but not exactly. There's some finite oscillations that maybe just go on forever. Is such a scenario allowed? Right? We don't really know this, and the physicists' level of analysis will never tell us what's really possible. So when I wrote the paper and when I've given other talks, people say, "Well, what are you not just making rigorous what we already know?" You'll see why people ask this. But I want to say, well, what do we really know? We have a very imprecise statement. You can find statements like this in the literature with various caveats in various ways, right? They'll have equal signs, and there will be tildes, and there will be arrows. There will be equal signs with a footnote, and so on. It's all a bit messy, and really that captures the fact that we're not really certain about what happens here. Okay, so what I want to ask is, can we make some mathematically precise statements and maybe exclude some of these scenarios in the process? Okay. Let me pause here for questions. People should just shout questions, because if this is not clear, then nothing will be clear. Okay. Let me stress that anybody, you can just raise your hand. It's fine. Just ask your questions. It'll derail my talk. It'll be fine. Your questions are more important than my talk. All right, so this should now be clear for everybody. So here's the outline for the rest of the talk. I gave the introductory part. I'll give you a bit of history and motivation. Why do I care about such mathematically precise things? Then I'll give the main results. That'll be the better part of the talk. And then at the end, there will be no time left, so I'll skip the modular bootstrap part. History and motivation. This is just one slide. It's this slide. So it starts about 13 years ago, where people did roughly the same analysis as I just did, like this physical level of rigor analysis, but they did it for conformal blocks. And that's why it's not a slide, it's an actual paper, because conformal blocks are harder than monomials. And that was done by these people, and also in parallel by this other group. And there are many follow-ups. These papers have each 500 citations or so. So it's important, probably for your general education, that you know what the lightcone bootstrap is. But there were no precise results. Let me scrap the word results and say there are no precise mathematical theorems of this analysis until 2022. And that's when these guys, they proved a little theorem for conformal blocks. I'm not going to state the result. The methods are also not particularly useful for generalizations. I have a new method that I want to talk about instead. But for 10 years, like, this was just accepted in the community, but the precise statement was never clarified. So since these works are apparently important, it's probably one motivation is just to ask yourself, well, can we do better? Can we get some precise answers out there? And maybe we can compare these answers with some other methods. We have the numerics. Numerically, we know spin 50 scaling dimensions nowadays for the 3D easing model. Can we compare the large spin analysis with what if at spin 50, right, you have these nice trajectories, so the numerics looks a bit like this. And what if at spin 50, the operator was just not there? And then at 52 and 54 and 56, and so it would be there again. Would that be a numerical mistake? Would you say, well, no, that's not compatible with the lightcone bootstrap? Or is that still allowed, right? So it would be nice to see if you can make precise results and then compare them precisely with the numerics. Another thing is the analyticity in spin. Another motivation is a follow-up paper basically from this, which is the famous analyticity in spin paper by Simone Caronio that Agnès also mentioned. Again, many follow-ups cited about 400 times now, I think. But there's a little caveat in this Lorentzian inversion formula story, which is that it relies on some benign light cone limit on the second sheet of the CFT correlators. I won't go into the details, but there's a little bit, some results, not all, but some results in this literature rely on some unproven assumptions. I think it would be nice to make that precise. So there's this famous, so let me stress that it's kind of a famous-ish open problem in the rigorous CFT community, whether we can understand this light cone limit on the second sheet. And what I'll present, I'm not going to explain, but what I'll present is a first step in that direction. And then in 2022, I wrote this paper, QFT in ADS instead of LSZ. Not many follow-ups, not cited hundreds of times, but still it's nice, I think. And this was my original motivation Right, I talked about this last year. So I want to prove, for example, the Froissart bound from CFT axioms. And again, you can go to my talk from last year to see, I think the slides at least are online. You can see what I want to do. But the Froissart bound is something rigorously proven, right? You start from the Weidmann axioms. If you want, you start from the lattice. The lattice, you can prove that the Weidmann there are theories that obey the Weidmann axioms. You can prove that they have an S matrix. You can prove that this S matrix obeys the Froissart bound. It's super rigorous. And now I want to see if we can do something a little bit easier, which just take the flat space limit of a QFT in ADS. So then I have the boundary correlators, they obey the CFT axioms, and maybe I can then prove the Froissart bound. So I think this is a nice target to aim for, but I need rigorous control. I need this light cone limit on the second sheet to be benign. And so to get this rigorous control, I need to understand this light cone bootstrap. So that was my motivation. Okay, so there's a lot of context, even though the problem is very easy to formulate. Okay, that brings me to section 2, which will be the bulk of the talk, my main results, and it'll rely on 3 theorems, a Taberian theorem, Vitali's theorem in complex analysis, and the so-called dominated convergence theorem, which you've all seen. I'm sure you've all seen it. I'm not sure you all remember it, but you've certainly all seen it. And so this part of the talk will be fairly technical. You should interrupt me with questions, but it'll give me an opportunity to explain these 3 things. So if you don't know any of them, then hopefully at the end you will, and you will have learned something, and you can go to lunch already a bit more fulfilled. And then, of course, the modular bootstrap part, yeah, that I'll skip. Well, maybe not, we'll see. So I have 3 classes of theorems to discuss, or 3 theorems, and I have to apply them, of course, to the toy lightcone bootstrap. So that's the thing I want to do next. So Taberian theorems. What are Taberian theorems? It's a useful tool. You should add it to your toolkit. So I want to explain what they are. And Taberian theorems are very easy to explain. You all know the geometric sum, right? This is very, very easy. And so this is trivial, but there's also a theorem, and this is the simplest possible Taberian theorem. And it says that if you just modify the coefficients arbitrarily, subject to a constraint that they're bounded from below, let's say positive for simplicity, or non-negative. I modify them arbitrarily, but I still demand that as x goes to 1, this function So this sum, I demand that it converges and that as x goes to 1, it behaves like this. And here I realized that I skipped something. I didn't include, I missed something in my slide. This is mathematical theorem. So there's a tilde, but it has a precise meaning. So the tilde a to b as c goes to d is really the statement that the ratio goes to 1. Okay? So that's what the tilde means. It means something mathematically precise. So okay, let's go back. The theorem says that if the limit is still like 1 over 1 minus x, then that rigorously implies that if I were to sum the coefficient just without the x, that's the same as just summing the 1. So that's of course lambda in the lambda to infinity limit. So it tells you that sort of the sum of the coefficients, or if you want the average of the coefficients, if you omit the factor 1 over lambda, is exactly the same as what you would get from the geometric series. Okay, so now you know what Taberian theorems are, or what a Taberian theorem is. So it's important that so you cannot say that the individual coefficients asymptote to 1. Here's a very simple counterexample: 2 times x to the 2k. The coefficients are 2, 0, 2, 0, 2, 0. On average, that is 1. And you can also check, or you can, yeah, if you're very bored, you can you can work it out in your head. But as x goes to 1, this also goes like 1 over 1 minus x. So it's important that you don't get an asymptotic behavior. You don't just get the asymptotic behavior of the coefficients. You only get the average of the coefficients. I should also say that there exists estimate of the error terms. There are many, many generalizations. You can have more general power. You can have exponential growth as x goes to 1. You can say, well, what if this limit holds not just along the real axis, but along any segment in the complex plane or whatever, right? These are, there's a nice book by Jaap Korevaar, a Dutch professor who actually passed away earlier this year. Who wrote that contains lots and lots of these Taberian theorems, right? So, but it's a useful tool. The one theorem that I'll need is, of course, I don't have integer powers, right? I have something like this. I have dk x to the h bar k, where x is now, you should think of it as z bar from the previous slide. So I have a sum like this, and as x goes to 1, it doesn't behave like 1 over 1 minus x, but it does something like 1 over 1 minus x to the delta, with some coefficient that I'm not including in the theorem here, but that will be imported on the next slide. And so there is a Taberian theorem, and we're going to use it. So this is the theorem. It says that if you have this behavior, then the asymptotic form of the coefficients is again precisely the same as if you were to expand the right-hand side into monomials. So here I have to truncate h bar less than lambda, and that's the same as summing here k less than lambda. Well, this right-hand side sum is very easy to do, and asymptotically as lambda to infinity, it's just this term. And again, this holds under the condition that these coefficients are non-negative. Okay, so we have a theorem in our toolkit. We can apply it. So here's what we know. This is, again, the third time I write this equation, so you should all understand it now. And our Taberian theorem that says, well, I'm going to think of the ck z to the hk as the coefficients dk from the previous thing, right? There's dk here, and x should be z bar. So it's cz to the h is the asymptotic behavior, and then there's this 1 over 1 minus z bar to the delta phi. So that is the dominating term on the right-hand side. The z bar goes to 1. So so it says that if I sum the coefficients, which are cz to the h, then I get the right-hand side, z over 1 minus z to the delta phi. That's just a prefactor, and then this same lambda to the delta over gamma. And you can get this for every z for which these coefficients are positive. So you get this pointwise for every single z between 0 and 1, right? Because that's where these coefficients are positive. So this is Taberian theorems. Taberian theorems, I already wrote it on my previous slide. They were first used in this paper for CFTs. So they're known in the bootstrap community a little bit, but I think it's a useful thing to know in general. So we have a Taberian theorem, and what we did is we basically killed the z bar sum, and we just wrote it in terms of a sum over h bar with some cutoff lambda, right? Pictorially, we have this h j thing, and we have some cutoff lambda at some h bar And we're just summing all the coefficients here, but there's still the z to the h. And that's a problem, right? Because we don't want the z to the h. We want to know something about the spectrum and the values of h that appear. We don't want the z to the h. So how do we trade the z for some h, right? That is the main problem of the lightcone bootstrap. And that's why the lightcone bootstrap is hard, because, well, for example, if you want to do, you can try to do a second abelian theorem and send also z to 1, but that loses information. Then you get something about the large delta spectrum of the theory. That's fine. You get some information. But the lightcone bootstrap, we want to keep z finite. We want to say something about finite h and large j. And this is why the lightcone bootstrap is hard and why there are no, very little has been proven for a very long time. And we also cannot expand around z equals 0. It looks okay, right? Z to the h, here you get z to the delta phi to the leading order, and then delta phi plus 1 and delta phi plus 2, and that was exactly the spectrum that I had. And so you would say, well, there must be operators with h equals delta phi, h equals delta phi plus 1, and so on. But that's not legal, right? If you have a pointwise limit, you cannot just start expanding and interchange limit. Z bar to 1 and z to 0 are very different limits, and you cannot just freely interchange limits. Right, so this expansion around z equals 0 is not something you can do rigorously mathematically. But there's one second theorem that comes to the rescue, which says, so in black, I basically had what I had on the previous slide. Sorry, this rho z of h bar should be this cz to the h. So I had what I had on the previous slide, and initially it's true that this is only true pointwise for z between 0 and 1. But in fact, the same statement is true in a much bigger domain. It is actually really, really big. It covers many, many different sheets in the complex z plane. If I take z equals r e to the I theta, so z to the h is r to the h e to the I theta h. So, right, I go to the universal cover of the complex z plane with this cut. Then this result is also true for r between 0 and 1 and any theta in r. So I can, like I sketched here, I can start somewhere here in the unit disk and I can go through the cut and I'm on the second sheet and the result is still true. And this is remarkable because I didn't even know that this first equation was true on that sheet. Because this first equation uses the T-channel OPE and the T-channel OPE stops converging there. So I wasn't sure about this first equation, but the second equation actually holds in the, and by extension, actually also the first equation, but a priori it's completely it was non-trivial. And the proof uses basically just the fact that this thing is an analytic function in Z, and if I go onto the second sheet, it's not going to blow up suddenly because I just insert phases in the sum. If I add e to the I theta, it's not going to make the sum any bigger because these coefficients and exponents are all positive. So, and if analytic functions don't blow up, then basically the limit is okay. That is what Vitali's theorem in complex analysis tells you. I have a bonus slide, which you can probably find online after the talk, where I state Vitali's theorem. But roughly speaking, that is the idea. So it's great. So we actually have a much bigger domain. It's not just pointwise. It is, well, it is actually pointwise. It's slightly better. It's uniform on compact subsets, but that's not important. But it holds for any r between 0 and 1, not just, and any real theta, not just theta equals 0. So that's great. We have a better result, and this unlocks some opportunities for us because, and now we'll just get to the dominated convergence theorem part, which is straightforward, but the equations look a bit messy, so let's go slowly. So this is what we know, right? I substituted z equals r to the I theta. I have this left-hand side, and as lambda goes to infinity, it looks like the right-hand side for all values of r between 0 and 1 and any real theta. Right? This is completely fine. Okay. And what I said, are there questions now? Okay. So what I said before is you cannot expand around z equals 0. That's the same as saying, well, you cannot expand around r equals 0, right? So if I want to know the values of h that appear, a natural thing to do here would be to expand around r equals 0 and see which powers I have, but that was illegal. So now I can ask you a question. What is another way to extract the powers of h that appear here? Right? And if you think about it for 5 seconds, it's actually very easy. I'm not going to ask you seriously, let me just give you the answer. How do I see the values of h that appear? Well, I just inverse Fourier transform with respect to theta, right? So I just do this. I Fourier transform with respect to theta. There's this factor r to the hk, but I just divide by r to the h. That'll do the job. And now I get a spectral density weighted with these OP coefficients. So that's great, right? So this Vitalis theorem, the fact allowed us to integrate all the way from -infinity to infinity. We're going on all the different sheets and so on. So without Vitalis theorem, we would never be able to do this. But now, because we have a result for all real theta, we can do the inverse Fourier transform. So, okay, great. Can we take the limit, right? So we say this, and then as lambda goes to infinity, this purple thing becomes the green thing. So we just plug it in. And, well, this integral is very easy. And this is the inverse Fourier transform of that. And that's just known. I basically wrote it on the previous slide. So is this true that this is now the result? And obviously it's not, right? Because I'm taking this is the limit of the integrand, but the limit of the integral and the integral of the limit are very different things. In general, limits and integrals do not commute. So oh, there's an E missing, sorry. But there's another important life lesson that integrals and limits do not necessarily commute. It may be a surprise to many people in the physics community, but it's definitely not always true. And here we see it very clearly, because this is a very sharp spectrum, and you would not expect this average spectrum this kind of thing to go exactly right. These are delta functions, and you wouldn't expect these delta functions to exactly become this at large lambda. So we're back to a few slides ago. We can take the inverse Fourier transform, but we don't know what the limit is of the integral, because we only know the limit of the integrand. So we have to soften, right? To see what goes wrong, why can't you swap in this case? A good example to have in mind is, for example, if this guy would be some bump function in the theta plane, and the bump would go off to infinity in the limit. Right? If you have a bump function in the theta plane, it integrates to say 1, and then as you take it to it doesn't even matter where you position it, but as you take it to infinity, the integrand for every point becomes 0. So the integrand becomes 0 pointwise, but the integral remains 1 because it always finds the bump function at some point. Right? So that's a good intuition to see what one of the subtleties that can appear. It's the most important subtlety in this case. And so what we can do is just suppress the stuff at infinity, right? So so that the bump function becomes smaller and smaller, and that'll cure the problem for us. And that's what we're going to use. So what I'll do is, instead of taking this inverse Fourier transform, I just integrate both sides against some weight function, var phi of h, phi of h. Of course, here it was delta function, so it just picks up the delta function. That's just phi of h minus hk. And here there's phi of h on the left-hand side that I integrate against, on the right-hand side that I integrate against what I had. Right, and phi of h is, if it were a delta function, I would be back where I started. But if phi of h, you should think of it as some bump function, some smoothed out delta function. Right, so for any finite lambda, it is fine to move to swap these two integrals. So I move phi of h inside the integral under some very minor conditions for phi. So you move phi of h inside the integral, and now you can ask, well, at least now can I say something? Can I say something about the large lambda limit? Is this known, and for what class of weight functions is this known? And here, of course, this is the dominated convergence theorem. It says that if your integrand is bounded by some nice, continuous, absolutely integrable function, then everything is fine. And in our case, that boils down to this condition. It says that if I take the Fourier transform of phi of h up to this unimportant factor r to the h, that should be absolutely integrable. Right, so you see that phi of h cannot be a delta function, because then this would be 1, that's not integrable. Phi of h cannot even be a step function, because that would be the Fourier transform of a step function falls off like 1 over theta, so that's not integrable. But it should be some smoothed out step function, and then we're good. So it's for these kind of test functions that I can swap the lambda to infinity limit with the integral, right? So this is the kind of result we can now prove rigorously. So here's our conclusion. We use 3 theorems, the Tauberian theorem, Vitali's theorem, and dominated convergence theorem. And we obtain a theorem of our own, a theorem of sorts, or proposition, if you want to be modest. It says that if we have this behavior, again, this is the 4th time I read it, so that you understand, then I have this result, right, for some class of test functions that obey this condition. So I have the OPE coefficients, I weigh the values of h with this test function, phi of h. I sum over all h bar, or all j, say less than or equal to lambda, and then as lambda to infinity, this must diverge as lambda to the delta phi, and then it has the known behavior from the right-hand side. Right, so, and as I said before, the test functions are not allowed to be a delta function because they don't obey this condition, not a block function that doesn't obey this condition, but something smooth, supported on some very small intervals, say 2 epsilon, that's totally fine. So for these class of test functions, I have a result. And so we can go back to our, so this is our main result, and we can go back to our picture and see what we have proven. Well, these first 2 scenarios are not yet excluded. Well, the first scenario is probably what happens. The second scenario with infinitely many gaps has not been excluded because I can have infinitely many gaps, but the coefficients of the other terms can be a little bit bigger to reproduce still this behavior, including the divergence lambda to the delta phi. But this third scenario where you have finite oscillations, that is now excluded, right? Because I can take, so I'm in the h direction is where I have my test function. So I can pick my test function to be a smooth bump function, but supported in some very, very small interval around delta phi plus m. Sorry, again, this should be delta phi plus 2. And if these oscillations have some finite amplitude, they never touch my test function. So then I will get 0, roughly speaking, from the test function contribution. But I need to get not 0, I need to get infinity. I need to get this particular divergence. So I need infinitely many terms inside the window where my test function has support. And that's also what this statement says. It says that for any epsilon greater than 0, any integer, non-negative integer, there must exist infinitely many terms where h lies in this little interval. Right? Infinitely many because I need this divergence, and every single term only contributes a finite number of terms. So this scenario is now excluded. This scenario, like I said, is not quite excluded, but in upcoming work we'll probably exclude it. And this is probably the right scenario. So now we have done the full analysis for monomials. It was actually fairly easy once you know the right theorems. In the paper, I do the same result for conformal blocks, or the equivalent result for conformal blocks. How do you say mutatis mutandis? The things, changing the things that have to be changed. But it's fairly obvious. Okay. So that's my main result, and now I have to go back to my motivation sheet and slide and say something about the lightcone limit on the second sheet, the Lorentzian inversion formula, and so on, and how things can be improved. Of course, I don't have the time for that, so I'll skip that. But let me take a step back and ask what we are really doing and what kind of research direction follows from this way of thinking. So I guess you can call it more or less averaging. In a certain sense, right, what are we doing? We have this kind of decomposition, maybe with conformal blocks, maybe with monomials. We know what happens as z bar goes to 1. And then for certain test functions, we show that if you take this OPE density, right, which is just the density of, well, here it's a monomial density, but you can make it for conformal blocks, it would be density of operators. You take this density, the density itself, I don't know what happens, but if I average in this peculiar way, where I integrate over h bar to some lambda, and then integrate over h with some test function phi, then I know what happens in the large lambda limit. right? This was my result. And now the natural question is, well, if you see this OPE density with some averaging is known, then it's natural to ask, well, what's the best? Is this the best thing we can do? Can we do better? How much of this averaging did we really need, right? This was me in 30 minutes explaining, well, 32 minutes, explaining to you exactly like the theorem in full detail. Can we work a little bit harder and get a better averaging? Can we, right, there are three important directions here. Can we, for example, so here we have an integral over h bar, and like I said, h bar is roughly the spin, so you should roughly think of it as a sum over all spins up to some cutoff lambda, and then we understand the lambda limit. But can we not just say, right, that, can we not just take a large J limit? That would exclude this second scenario, right? Because if this would be, if we would have a result for the large J limit, then we would say, well, no single spin can misbehave asymptotically. There cannot be asymptotically many gap because every spin has to fall in line eventually. Or another thing that would be nice is whether this phi of h can be J dependent, right? Phi of h cannot be a delta function. But it would be funny if phi of h would look more and more like a delta function as J increases. That would be a possibility, and you can ask, well, can we improve in that direction? And then, of course, I mean, I have a limit, so I can ask, well, what about subleading correction? How fast do I approach this limit? Can I understand some of that? Right. So this is the I think the main question. And you should ask this question every time people have these kind of, right, these wiggly equations with tildes and these imprecise equations. There's a whole range of possibilities of what these tildes really mean. And it's possible to make them precise and actually get interesting results. And so for the modular bootstrap, like, yeah, I don't have time, so I'll skip that. We answered all these questions in the affirmative way. We got some. We can we can replace the limits of the sum with just this limit. We can make test functions shrink in a particular J-dependent manner with the rate that you can find in the paper. We can say something about the rate of convergence and so on. So this I'll skip. For the modular bootstrap in this paper with Friedrich and Yashin and me, we have a proper theorem, and you see here the Virasoro primary density averaged with some J-dependent test function in the large J limit, no sum is known. And then, oh, there's some, and I know there is something about the rate of convergence. So that's the main result of the modular bootstrap that we have. And we have some corollaries that I'm not going to talk about. So let me stop here. Thank you very much.
There's one question here.
Is there any test function dependence? Like if I take, say, two bumps that come together while they're also being thinned at the same time? Or like?
Yes, but my statement is, my theorem is just true for any test function, right? Of a particular, in a particular class, sorry, this was the wrong direction. Right? If you pick the test function, you pick whatever you want, right? This result is still true, right? If you have two bumps, you pick up two. Here on the right-hand side, right? You see that the right-hand side only depends on the support of the test function, the delta phi plus an integer. So it's at these points. So if you have two bumps, you pick up two terms. You just get two terms in the sum that contribute. If you pick a single term, you get a single bump. So you get the test function. If it obeys this, then my theorem is true.
I was just wondering because you couldn't replace it with a delta function. So maybe would the result depend in how you approach the delta function using different test functions?
Yes. So sorry, here the test function does not depend on J. Test function is given, it obeys this. If it does that, then the result holds. In the other, here I had a J-dependent test function, and you should look at the paper at the particular rate at which this becomes a delta function. It cannot be arbitrary. There's a power which is J to the 1/4, which enters here essentially. Yeah.
Hello, thank you for the talk. I was wondering, usually when you use Tauberian theorems, there is a problem in deriving rigorous asymptotics for the OP coefficients, which is given by the fact that you are always averaging over the OP density, spectral density. And you cannot really integrate on a small window because the rigorous result is always for the large, from 0 to infinity. But here you seem to have a leverage, like a handle on the spectral density itself. So I was wondering if,
Yes.
like you are using a test function, not the delta, but is there any hope to find a rigorous asymptotics for large lambda for the OP coefficients?
Yeah, I think so. If the talk had been longer, I would probably announce the death of Taberian theorems as a useful tool. But it's, as a first order, it's very good. It's very useful. But I think on the longer term, right, we know more, right? If I want to fish out what happens at particular spin J, here in the modular bootstrap, it's very easy. It's just an inverse Fourier transform of the partition function. So I have this modular invariant partition function. I do an inverse Fourier transform. Right, and then as J goes to infinity, I pick things so that sort of there's a particular limit that dominates, and then everything is fine. But these Taberian theorems, their only assumption is that I know what happens. Well, let me just not go to the slide. Their only assumption is that you know what happens as x goes to 1. But for the CFT correlator, I know much more. I know the limit as z bar goes to 1, but if you want to give me an estimate that z bar equals e to the I theta, I can give it to you. It may not be great, or z bar equals -1, right? I use all my OPEs and everything at my disposal. I can give you those estimates. And so we should probably not be using Taberian theorems on the longer term, because we should just write these integrals directly that fish out, that project onto a particular spin J, and estimate those integrals using whatever S-channel, T-channel OP coefficients that we have at our disposal. And in this result, we do, in the modular bootstrap result, we do actually, we use not just modular here on the right-hand side to get the result. We don't use the decomposition in the cross-channel of the modular invariant partition function. But for various terms that might potentially be dangerous here on the right-hand side, we actually go back. We use modular invariance again to estimate that they're small. And therefore, they don't show up here. But to show that they're small, we had to use modular invariance twice. Yeah. Yes. Well, thanks. These are my corollaries. So for the modular bootstrap, because here they come with coefficients 1. Of course, for the CFT bootstrap, right, you're not just counting states; they're weighted by OP coefficients. And if you have a coefficient of very 10 to the minus 100, I will never be able to fish that out, or something decreasing with J. But here the coefficients are 1, and indeed we know that the spectrum becomes dense at very large spin because this right-hand side has a dense spectrum, and it becomes dense for every large spin in some sense, right? There's a proper limit. There's no spin where no spin can misbehave, and we know the rate at which it becomes dense because that's basically the inverse of this in the average. But because we have some convergence here, not just pointwise, but uniform in H space, uniform on compact subspace in H space. We actually can bound also the maximal gap between two operators. And we have a pretty weak estimate, but I think it can be improved by a lot, but we have a proper estimate on the maximal gap between two operators. So it's not just an average statement anymore.
Thanks. I don't see any further questions. So let's thank Balt again for the beautiful talk.